you are interested in determining the strain rate of deformation, then this is the following approach. This is the approach that we are going to use. So, most creep mechanisms, either they happen by diffusion of vacancies or they happen by that they involve dislocation motion. So, now for the derivation of the creep strain rate equation, let us assume a simple case. Simple case of dislocation overcoming barriers. So, if you remember in the previous lecture, in one of the slides I was talking about the barriers to dislocation motion or barriers to plastic deformation, and we were talking about two types of barriers. You have, just as a recall, you have short range barriers and you have long range barriers. And short range barriers, if you remember, we said it is possible to overcome these barriers by thermal fluctuations alone. So, if the barrier is such that just a temperature just thermal energy by providing thermal energy you can overcome the barrier. Now, for the case of dislocation overcoming barriers, we are going to talk about a simple case of dislocation overcoming a short range barriers. Now, one of the things about thermal fluctuations is thermal fluctuations are usually random in nature. These are random in nature. So, it is a stochastic process and they can activate, the thermal fluctuations can activate only a relatively small number of atoms, and that is why it is a short range barrier, right, because we said short range barriers are those where the atomic distances involved are typically a few atomic diameters, maybe a couple of atomic diameters or 5 atomic diameters, whereas when you talk of long range barriers you are talking distances which are significantly larger, maybe 300 or 1000 atomic distances. So, thermal fluctuations can activate only a small number of relatively small number of atoms and the distances are small. So, example, if you remember, so one of the examples is removal of an atom from an edge jog in a screw dislocation for the climb of the dislocation. So, for the dislocation to overcome the barrier, it is an energy barrier, the energy is being provided by thermal fluctuations. So, let us now look at a simple diagram. So, say this is a barrier, you have position A and say position B. To go from position A to position you have position A and position C. To go from position A to C you have to overcome a barrier and the top of the barrier is position B, and position A and B or points A and C represent free energy minima. So, the material, the dislocation is in a low energy condition or in the configuration at both points A and C, and it is now trying to go from A to C. It favors either in either case it is comfortable, whether it is in A or in C, because the free energy is low. So, it is comfortable, but it has to overcome this energy barrier described by point B. Now, a single operation. So, if there is a mechanism, there is certain mechanism which helps the dislocation overcome this barrier. So, a single operation of the deformation mechanism takes the dislocation from A to C. So, because the dislocation is moving from one point to another point, so there is going to be some amount of plastic strain associated with it. So, because of this motion, so the crystal experiences a small strain, and the direction of the strain depends on whether the dislocation is going from A to C or from C to A. In this case, we are talking about the dislocation going from A to C. Now, let us assume the case where a stress is acting in the direction which pushes the dislocation from A to C. So, there is a stress which is trying to push the dislocation in this direction, and we know that typically strain will be in the direction of stress, and so positive work is performed here. So, work is performed and this is positive work. So, the stress is making the dislocation move, there is some strain that is generated in the process. So, you have stress and strain, the product of that will give you energy. So, this is equivalent. So, basically because of the presence of a stress, what is now happening is the energy barrier is getting lowered. So, this is B, this is A, and this is C. So, the original, with respect to the original locations, A has moved up. So, say by a quantity W1, that is the work performed, and say C has come down by quantity W2, and the activation energy barrier. So, to go from A to B, there is an energy barrier, and let us say we define it as Q. So, now because there is some amount of work that is getting performed by the application of a stress. So, Q is going to, Q remains the same, but the activation energy barrier for moving from A to B is going to come down. So, it is going to become Q minus W1, and because the system is driving, because the presence of the stress is driving the system forward. So, it is going to become even more difficult for an dislocation to move in the opposite direction. So, C is going to come down, and so now the barrier for the dislocation to move from the new position of C to B will be Q plus W2. So, in the derivation of the strain rate equation, we are neglecting entropy effects. So, we are talking about point 1 and point A and point C, and we said they are at a low energy configuration, both A and C. So, when A moves, when the dislocation moves from A to C, we are talking about a free energy change, and generally when we talk of free energy change, we say delta G, and delta G is delta H minus T delta S. So, this is the enthalpy change and this is the entropy change, but in creep conditions people generally ignore the role of delta S. So, whatever free energy change that is happening is generally described in terms of delta H only. So, the strain rate, we are neglecting entropy effects. One of the reason of neglecting entropy effects is because their role is not well understood. So, coming back to the drawing. So, you have the situation. So, A to C in the presence of a stress. So, the change in energy is W1 when the mechanism operates from A to the activated state B, and the change in energy when the dislocation mechanism. So, when we talk of mechanism, we are talking about the dislocation mechanism, the mechanism by which the dislocation is moving. The change in energy when the dislocation mechanism operates from C to B is W2. So, the moment you climb up the hill, so say A, the dislocation climbs up the hill to B, then it is going to easily go down to C, because that is law of thermodynamics. So, it is going down the energy barrier. So, it is going to be easy. So, for A to move to C, the energy barrier effectively is, so the energy barrier for moving from A to C is effectively Q minus W1, and the energy barrier for moving from C to A is effectively Q plus W2. Now, from reaction rate kinetics, it is known that the frequency of operation, from A to C is given by nu 1 is equal to nu naught e to the power minus q minus w 1 over k t, and the frequency of operation from C to A will be nu 2 is equal to nu naught e to the power minus q over plus w 2 over k t. So, this is coming from reaction rate kinetics. So, B is the activated state. So, A in reaction rate kinetics, when you are talking about two reactants reacting with each other to form the product. So, they go through an intermediate stage, which is the activated stage, before they reach the product stage. So, similar thing here, similar concept at work here. So, the in general the frequency corresponding to strain in the direction of stress will be larger than that opposed to the stress. So, since the stress is aiding in the dislocation motion, so the probability of the dislocation moving from A to C is going to be higher than the reverse of it, which is coming back from C to A. So, that is because of the presence of the stress. So, if a large number of identical mechanisms are operating. So, imagine a large number of dislocations moving and in this fashion are operating in this fashion, then the net rate at which creep strain occurs. So, the net rate at which creep strain occurs is going to be, so this creep strain rate, net rate is going to be proportional to the difference between the forward and the reverse frequencies. So, we are talking about thermal fluctuations, we said it is kind of random. So, for the dislocation could go from A to C or it could come back from C to A, both are possible, but when you have a stress present, then the stress is going to the motion of the dislocation is going to be in the direction of stress. So, there will be the number of jumps possible from A to C will be higher than the number of jumps possible from C to A. So, the net strain rate of deformation is going to be dependent on the number of forward different jumps minus the number of reverse jumps. So, in this particular case, so you can say strain rate of deformation is going to be approximately a difference of the number of forward jumps minus the number of reverse jumps. So, since nu 1 and nu 2 have already been given, so it is going to be nu naught e to the power q minus W 1 over k T minus e to the power. So, this makes strain rate is equal to some constant e to the power minus q over k T into e to the power W 1 over k T minus e to the power minus W 2 over k T. So, then strain rate becomes A e to the power minus q over k T into e to the power W 1 over k T minus W over k T e to the power minus W over k T. So, if you know the hyperbolic sine function sin h is e to the power x e to the power minus x divided by 2. So, if we invoke that here, then strain rate becomes A e to the power minus q over k T into 2 times sin h W over k T. So, here sin h x is equal to e to the power x minus e to the minus x by 2. So, we invoke that here. So, then that makes epsilon dot is equal to A e to the power minus q over k T into 2 times sin h W over k T. So, we can take 2 into A. So, then that becomes basically it becomes strain rate is equal to epsilon dot is equal to A e to the power minus q over k T into sin h W over k T. So, the work done W can be basically described as a product of the activation volume V into the stress acting tau star. So, V is the basically W can be considered a function of tau star. So, this makes strain rate is equal to A e to the power minus q over k T into sin h some function of tau star by k T. So, what we have arrived at is basically a relation between the strain rate of deformation So, we are getting a relation that strain rate of deformation which is a function of tau, the function of temperature T as well as the applied stress tau. So, this is a very important equation that we have arrived at, and we are going to come back to this equation in a slightly different form. So, we are going to look at this equation again. So, this equation is at the heart of creep deformation. So, it basically tells you the relationship between the strain rate of deformation and temperature T and the applied stress tau. There will be slight variations of this equation, but the concept is going to be the same. So, here we were talking about the forward and the reverse frequencies, but so here we were talking about the forward and the reverse jumps, but if under certain conditions. So, under conditions where Q is very large, so the activation energy of deformation, say it is very large compared to kT, and if the applied stress which we considered as tau star, if the applied stress is also large, then the backward frequency of deformation nu 2, the backward frequency of deformation mechanism nu 2 will be small. So, in that case what would happen is the mechanism acts only in forward direction, and epsilon dot is going to become A e to the power minus q minus w over k t, and that becomes epsilon dot is equal to A e to the power minus q over k t into E to the power w over k t. We already said w is activation volume into tau star. So, that makes it A e to the power minus q over k t into e to the power nu tau star over k t. So, this is another form of the equation. So, strain rate as a function of temperature and tau star. So, this describes the dependence of strain rate of deformation on temperature and stress. So, in general, the energy barrier of a typical dislocation reaction. So, we are talking about the energy barrier Q. So, in general, typical dislocation reaction, the energy barrier is of the order of 1 electron volt or larger. So, at room temperatures, the thermal fluctuations provide energy of the order of 1 by 40 electron volt, and at high temperatures, say around 900 degree centigrade or so, the thermal fluctuations provide around 1 over 10 electron volt. So, what this tells is that as you keep going as you keep increasing the temperature, the energy provided by thermal fluctuations is also going to increase, and that is why it becomes easier for the dislocations or the defects to the dislocations to overcome the energy barrier at higher temperature. So, of course, since the contribution from thermal fluctuations is around only 1 over 10 electron volt, it is only smaller compared to the barrier height. So, you also need stress to play a role. So, that is why both stress and temperature together will help you in help the dislocations overcome the barriers to plastic deformation, and that is how both have a role to play.